Okay, questions? It was question, yeah, it was 86. So this had to do, question 86 had to do with, it had to do with the IHDs, the indexes or index of hydrogen deficiency. And there's two ways to do the, so they say, oh good, then I don't have to say index of, I don't have to say index of hydrogen deficiencies anymore, because in parentheses it says degrees of unsaturation, which is what I call these things. So either term, what it is this is a way to get actually quite a bit of information from just the molecular formula. And so if you have nothing other than a molecular formula of a molecule, you can actually tell quite a bit about it. And that's using the degrees of unsaturation or the index of hydrogen deficiency. And so let me just give a quick context to this, because I don't think the book did a very good job of giving you context. It's one of these foreshadowings to lab next semester. We'll talk about this in Organic 2 lab when we talk about spectroscopy. But in essence, what it means is if I have methane, or if I have ethane, where molecules that only have carbon-carbon single bonds, if I looked at their formulas, they would have a formula of CnH2n plus 2. So methane 2 times 1 plus 2, ethane 2 times 2 plus 2. So in other words, this formula is what's called saturated. So you have the maximum number of hydrogens per carbon. And that's what the term saturated means in organic. So alkanes are saturated. Once you form a ring or include a double bond, you now have less than the maximum number of hydrogens per carbon. So for instance, if I wrote a cyclohexane ring, the cyclohexane ring would be C6, and then since each one of those carbons has 2 hydrogens, it would be C6H12, which is not C6H14, which would be the maximum number. So every time you have a ring, you lose 2 hydrogens off of the maximum number. And so if you had a ring with a double bond, then you would have a C6H246810. You would have a C6H10, which would basically be 4 hydrogens from the maximum. So that's these molecules would be considered they would be considered as unsaturated. Uh-oh. I guess you can drag that one to wherever it needs to go. Okay. Are you sure? So that's an unsaturated molecule. So saturated, maximum number of hydrogens, unsaturated, less than that. And those terms come about in, I think I've said this in here, saturated and unsaturated, we talk about fats or oils, or basically that's because let's start again. A carboxylic acid with a long chain that has all alkanes is called a saturated carboxylic acid. And when you make an ester out of this, you make a fat or a triglyceride. And so if all the chains have single bonds, it's saturated. If there's a double bond in there, it's unsaturated, right? So I think the saturated stuff will be what kills you. And then the ones that just have double bonds are unsaturated. I don't know whether they're good or bad. I think every month somebody comes out with a different study. Then if you take the double bond, you try and make a single bond out of it, and you don't do that, you get partially hydrogenated, which are death apparently. So that's where the terms come from. But this formula then, these formulas can be used to calculate what are called the degrees of unsaturation, or IHDs. And basically the formula that I use is the number of carbons minus the number of hydrogens over 2, or 1/2 the number of hydrogens, plus 1. The number of hydrogens could also be the number of hydrogens plus the number of halogens, because a halogen replaces a hydrogen in the structure. Oxygens don't count, and nitrogens end up giving you like 1/2 of a term, which I'm not going to worry about. So with just CH and O, with O not counting in this formula, this is how you can calculate the degrees of unsaturation from the formula. Is by figuring out C so many, H so many. Now the problem the other problem is if you got the structure, just calculate the number of rings and multiple bonds. So that was the problem in the textbook, dealing with, and there was a typo with one of these where it was said 8 and it should have been 4. I think their calculation, I don't know, somebody didn't proofread that very well. But it's an online book, and if I email them, they'll change it it'll just change right before your eyes. You'll go in one day and it'll be this, and you go in the next day and it'll be that. So I haven't done that yet. This was the molecule. That was how many indices of hydrogen deficiency are there in this molecule? And so what you can do is you can count the number of rings and double bonds, or rings and multiple bonds in that molecule. So, no, not the YouTube. Let's try that again. Print screen. So with this molecule, then we can count the number of multiple bonds and the number of rings. So what I think I showed was how many double bonds do we have in this molecule? 5. So we've got 1, 2, 3, 4, 5. So we've got 5. So we've got 5 carbon double bonds. I put the X in there because it's CO or CC. Then how many rings do we have? And so we definitely have a benzene ring for 1. Okay, so benzene itself has a ring and 3 double bonds, which means it has a degree of unsaturation of 4. So one of the things that's useful is if you had a molecular formula and somebody said, are there benzene rings in this? Is this an aromatic compound? If you got degrees of unsaturation of 4 or higher, it could have a ring. If it's 3 or lower, it can't. So that's a real quick screen as to whether or not there's a benzene ring in your molecule. Just because it's 4 doesn't mean there's a benzene ring, but next semester when we talk about spectroscopy, there'll be certain peaks that show up that are definitely for a benzene ring. And then how do we handle the bicyclic compound? Well, if it's bicyclic, how many rings is it made of? It's not tricyclic, it's not monocyclic, it's bicyclic, so there would be 2. And if you wanted to see those 2, we would have this is 1 ring, and then on the other side, the nitrogen, then down here, that would be the other one, and 2 of the sides are shared by both rings. So in this case, there's a grand total of 1, 2, 3 rings. So 5 double bonds, 3 rings, gives you a grand total of 8 degrees of unsaturation, or 8 indices of hydrogen deficiency. So you can do this if you wanted to. You could count up all the carbons, all the hydrogens, the nitrogen, the oxygen, look up the nitrogen formula, and it would give you the degrees of unsaturation that way. So the only thing here is the bicyclic compound. How do you handle it? But you can get a lot of information from the molecular formula. And I'll give one more example. If you had a molecule and you knew its molecular formula contained carbon, hydrogen, and oxygen, and it had 0 degrees of unsaturation, then you would know there's no CO double bond in the molecule. So that would mean that it's either an alcohol or it's an ether. And so you could tell that immediately about the molecule just from its molecular formula. And in lab, we'll talk about, well, where does the molecular formula come from? It comes from actually the molecular weight, because there's only certain combinations of molecular formulas that add up to a particular molecular weight. And that's what we use mass spectrometry for. So that's kind of the context. They're foreshadowing into January. I don't know how effective that is, but we will do this again. Plus, I guess it's also a review of looking at structures and trying to, how many rings are in the bicyclic compounds, etc. What else?
Can we do an example of a problem with naming organic compounds with multiple functional groups?
Sure. What functional groups would you like? Well, does everybody understand amines? How to name the amines? Should I include that in my as a functional group? Okay. Well, let's put a double bond there. Let's put an amine here. Let's attach to that amine. Here, let's do that. Then, just for the sake of argument, let's add a bromine. Anything else we want to add in here? Let's see, where is my list? Where's my functional group list? Just to keep things regular, let's do this. Let's put a triple bond in there. Okay. So I made all the functional groups lower than an amine, because once we make them higher than an amine, then the name switches, so we'll deal with amines first. So I got a double bond, I've got an amine, and I have a triple bond. So alkene, alkyne, and amine. So first thing I got to do is I got to look at my chart to see who has the highest priority. And when I look at that, I see amine is higher than alkene, which is higher than alkyne. Okay. And so that's our priorities are going to be set towards the amine, since it's the high priority. Now, when the amine is the high priority group, there is a way that we name it. And the way that we name it is we go to the nitrogen and we look at the three groups that are attached to the nitrogen. The longest carbon group that's attached to the nitrogen is going to be the parent chain. So looking at this is going to be my parent chain. And I'm going to handle that parent chain exactly like I have other parent chains. But that's how we decide with amines. So the first thing is, if the amine's the highest priority, the longest group, one with the most carbons, is the parent chain. Then what alkyl groups are attached to the nitrogen? Well, over here, what do I see? I see a 1, 2, 3 carbon chain. So I see a propyl group attached to the nitrogen. And over here, what group do I see? Ethyl. Now, bless you. These groups are going to go back into the list that I'm going to alphabetize of substituents. But I need to tell you that those groups are attached to a nitrogen. So what happens is that normally we've had a propyl group or an ethyl group with a number in front of it. Well, in this case, there's not going to be a number. There's going to be an N. So these are going to be N-propyl and N-ethyl. And so the N-propyl and the N-ethyl indicate that those two groups are attached to the nitrogen. So they're replacing numbers, basically. So now they go into the list to be alphabetized, along with what else? Well, it's a boring problem because what did I make it? Just a bromine. So I'm going to have a bromo group. So I'm going to have a bromo, an N-propyl, and an N-ethyl. Those are going to be my groups. So now I got a number. So remember, if you're the highest priority functional group, what does that get you? That gets you priority in the numbering, and it gets you the last suffix in the name. So the nitrogen is going to have the highest priority in numbering. So let's see if I did this. Well, I probably did this so that what would happen? It's a tie. It's not? So 1, 2, 3, 4, 5. 1, 2, 3, 4. Good. We can deal with what would have happened if it was a tie, I think, when we're done. Okay, so the triple bond and the double bond don't come into play unless there was a tie. And if you're thinking, well, what if there was a tie? Who would win out of a triple bond and a double bond? I believe it's the double bond would win. If I remember what the blue book says. The blue book says the double bond should get the lowest number before the triple bond. Actually, what it said is when there's just double and triple bonds there, you should choose from the end that's closest to the substituent. So, good thing we don't have to do that here. So, what do I have? I have a 3-bromo, an N-propyl, and an N-ethyl group as my substituents. So, alphabetizing them on E, P, or B. Those are going to be how I'm going to alphabetize. So let's go ahead and write that out then. 3-bromo, N-ethyl, N-propyl, and then we have to do the parent name. So the N's are replacing numbers, and so they're not part of the alphabetization. The other thing we can say is the N-propyl's hyphenated. We never alphabetize on the species before the hyphen. Okay, so this is our alphabetized list of substituents. Now I need the parent name. So how do we structure the parent name? First of all, first thing is total number of carbons, which is 8. So this is an oct. Okay. Then is it an alkane, alkene, or alkyne? It's both, an alkene and an alkyne. So then we have to go back and remember what it said about when there's a double and a triple bond in the molecule. When there's a double and a triple bond, stop. It's an ene ine with neither one of those looks like an ene-ine. That's what it is with the triple bond and the double bond. So double bond comes first, triple bond comes last. That's the anomaly in the numbering scheme. So it's an ene-ine, which means that the ene is going to come first. So it's an oct. What number is the double bond at? 6. Ene. The triple bond is at 1. So it'd be an oct, total number of carbons. Then because it's a double and a triple bond, that comes ene-ine. I'm not done yet. Because now I've got the last substituent.
I thought that the double bond had higher than
No, not in the cases in the book. The blue book specifically says that when you have a double and a triple bond, it's an ene-ine. So that's the anomaly in this. Yes, the double bond normally has priority, and for some reason, they've decided to call it an ene-ine instead of an ine-ene. Okay. And I'll be honest, when I just wrote out a draft of putting the table all together, the one that you can use. I'm going to put double and triple bond ene-ine. Because otherwise you'd have to look it up, so you'll have that chart to look up. Okay. All right. So I'm not done yet, because the highest priority group was the amine. So now I need a number to tell me where the amine was. The amine is at carbon 4, and then its suffix is amine. And if I go back to the table, you'll see that it's amine. So that's the name of that molecule. We've got the double and the triple bond in it. We've got the amine in it. We have the groups that are attached to the nitrogen of the amine, and then one single substituent.
So it has it on the table. It's in parentheses amine, and then there's like as.
I have never heard of azami or azanol. I've never heard of those terms. All that's going in your chart is amine and amino, if the amine was not the highest priority. So an imine is something else. An imine is next semester. So it's just an amine. But since it's the high priority, each one of these functional groups has its own little idiosyncrasies. And this is the idiosyncrasy for amine. When it's the highest group, you basically find the longest chain, that's the parent chain. The other two things become N-alkyl groups. They get thrown into the list, and then you go from there. Okay. So that's what happens. So that would be the name of this. Everybody okay with that? Can I... I just want to show you one other little idiosyncrasy with this molecule, and will it let me erase? It certainly will. I'm basically going to draw this molecule again. I'm going to add a group to it. And I want everything else gone. So I want to start with that molecule again. Okay. What I would like to do is I would like to add an ethyl group somewhere in this molecule so that there's an ethyl group attached to nitrogen and an ethyl group not attached to nitrogen. So how about I do this? So I just, same molecule, only I'm going to add the ethyl, I'm going to add another ethyl group to show you how you would handle this situation. So again, the same longest continuous carbon chain. I had to be careful that I added diethyl not to somehow make a new chain. So in terms of my substituents, I have an N-ethyl, an N-propyl, now an ethyl, and a bromo. Now, when you have two types of ethyls, when you have one that's attached to nitrogen and one that's attached to the chain, I'm still going to gather those up. So these two are going to become a diethyl in the naming. But the question is, so what goes in front of the diethyl? I don't think I changed my naming scheme or my numbering scheme, so it's still 1, 2, 3, 4, 5, 6, 7, and 8. So I have an N-ethyl and a 5-ethyl and then a 3-bromo. Okay, so the numbering scheme didn't change. If N is like a number, that diethyl is going to be N5 diethyl. So the N5 the significance of that is that there's an ethyl group attached to nitrogen, and there's an ethyl group attached to the chain at carbon 5. So we can have N's mixed with numbers if we have the same substituent. Okay, so we gathered up similar substituents before, and now we're going to gather them up, but one would be an N, and then the other would be 5.
Does it matter which one you put first? Should it be the first one in the chain that you find, or does it?
Technically, it should be an N. It should be N first, and then the numbers afterwards. If you put 5N, I probably will accept that, but it should be N5.
So, like, say if the mean was at 6, you would still do N5.
Well,
Well,
if
it
this
would
not,
change up the number.
if it would change up the numbering scheme. So all we're saying here is, when I read the name diethyl, I'm going to say there's an ethyl group attached to nitrogen, and then there's an ethyl group attached at whatever the number is
Okay.
in the chain.
But the N will always go first.
Yeah. So the N is really replacing a number. So that's what happens when you have the same alkyl group attached to nitrogen as attached to the ring, or as attached to the longest chain, sorry. So that's kind of how we do the multiple ones. Are we okay with this? Because we're really now at the stage where we have to do multiple ones that are going to have multiple groups. We can try another one. Let's see. Do I want to make it? Let's deal with one issue here with amines. What if they have something higher than themselves in the chain? How would you handle that? So, what if we had this? I'll put an aldehyde at the end. And then I'll put now I have to remember what system I'm going to be under here. Do I want to do this? I don't know that I want to do this. I don't want that methyl. I don't want a third methyl group. Okay. Okay. So now the amine's been supplanted as the highest priority group. So I've got an aldehyde and an amine. Now you might say, how did you know that? I'd have to go back to my chart. My chart says an aldehyde here, the C double bond OH is higher than amine. So the aldehyde wins. And if you're looking at this chart, one of the things that you see is all the groups that are automatically have to be at the end of the chain are all given those higher priority seats. Carboxylic acids, amides, esters, aldehydes. So anything that has to occur at the end of the chain gets some of the upper priorities. So in this case, even if I didn't remember that, I would know that the aldehyde beats the amine because it automatically has to come at the end of the chain. There's no way to make an aldehyde that doesn't come at the end of a chain unless you attach it to a ring, which we're not doing at the moment. Okay, so this is going to be then an al. So longest continuous carbon chain is going to be this one. That's going to be a 1, 2, 3, 4, 5, 6, 7 carbon chain. But I can go ahead and number it because the aldehyde takes precedence simply because it's at the end of the chain, so it automatically becomes number 1. So number 1 through 7. Substituent-wise, what do I have? Substituent-wise, what I have is have a bromine at 5, so this is a 5-bromo. And then at carbon 3, I have a dimethylamino, because now my nitrogen is no longer the high priority. So I have to look at it, and when I look at the nitrogen, it goes from being an amine to being an amino group. So now it's an amino group. So now when I go back, I have a 3 amino group, but I still have attached to that nitrogen, I still have an N dimethyls. And there were a couple of systems that they used for this. I believe the current Envogue system is this. Anything when you have an amino, the amino is going to come first because it starts with A. But the NN, anything with the N's has to come at the beginning of the name. So the beginning of the name here would be NN dimethyl. Where is the amino group, the nitrogen group attached? 3 amino. That beats bromo, so then a 5 bromo alphabetically. So we have an NN dimethyl, 3 amino, 5 bromo. If I'm reading through that and I see the 3 amino, I need to look for the things with the N's. I know the amino's attached to the chain at 3, that's one position. What's attached to the other positions? If there's 2 N's, both those groups are attached to nitrogen. If there was just one, it would be that group and then a hydrogen. Or if there were 2 hydrogens, it would just be amino. So this is an NN dimethyl, 3 amino, 5 bromo. Now the parent name. So it's got how many carbons? 7. So this is going to be a hept. Is it a alkane, alkene, alkyne? There's no double bonds in the longest chain. In the parent chain, it's only single bonds. So that means it's a heptan. This is an aldehyde, right? So I look at the chart and I say, what is the suffix for an aldehyde? It is Al. Do I have to say it's 1 Al? You can, but you don't have to. IUPAC would frown on that because it automatically has to be number 1. So you could just say this is a heptanal. And by definition, the aldehyde has to be at carbon number 1 in the chain. So this one would be NN dimethyl, and then the amino, those groups are attached wherever the amino is attached, wherever the amine's attached. But if it's not a high priority group, the amine. It's not a high priority group, the amine becomes amino.
So if the amine is not a high priority group, the ends come at the beginning of the
I believe that's the rule. Unless somebody wants to say the book says different. I'm totally going on my memory here, which isn't what it used to be.
Does that only happen for amines, or does that happen
That they have ends, or they go at the beginning. Only ends. Only things are attached to nitrogen, only when there's an amino group. When it's amine as the final group, the ends get put into the alphabetical order. And it could be, although I hope not, it could be that the dimethyl somehow went into that order as well. Although in one of the systems, it always came at the beginning. So that's an idiosyncrasy for amines when they are not the high priority group. We haven't dealt with it. What else do you have? Yes.
The question I think was like 36 was, it was the one where I was on top half actually, it was in 17. Was that just that the top hat had it wrong?
Yes.
Because we had it as 4 and it was like 8.
They had it as 8, we had it at 4, we're right. We're right at 4.
Okay. I just didn't know if I was reading it wrong.
No, they did it wrong. And that question's been asked. So one of the things is I answered it twice on Piazza. It's fine if a duplicate question gets asked, I just cut and paste my answer from the first one. So, but it is incorrect. Their calculation is incorrect, and I don't know how they did that. There was another one where they said, where when you clicked on the answer it said saturated, and then in the answer they said, well, this is unsaturated. Okay, another mistake. I mean, you can submit that mistake if you'd like. There's a form at the end of each chapter to submit mistakes. I don't know if they'll take it any better from you or me, but so this is the equation that they had. 1/2 the parentheses of 2 carbons plus 2 minus hydrogens. If you multiply everything by 2 there, you get my equation. So it's the same equation. And sadly, they don't even have the halogens in there. There's another form for nitrogens, but
I think they have it lower.
yeah,
Chapter.
I'm sure it is. Oxygens don't count. Halogens count as, yeah. So that one's, yeah, so if I multiply everything by carbons plus 1, number of carbons plus 1 plus the number of nitrogens minus 1. There's a factor in there. So we'll do those next semester. And I don't even know that I mess with nitrogen ones. And then there's the one for the halogen. So equation 2.2 is the penultimate equation. Except it doesn't have sulfur in there, but we're not going to do anything with sulfur. Okay. So that is just simply determining number of rings and double bonds. If I was to think about giving a question like that, I might just give you a structure to make sure you can handle the rings and the double bonds in the structure, as opposed to the math of the molecular formula. Rings and double bonds. Sure. You want a bicyclic ring or just a regular ring? What's the degrees of unsaturation or the indices for this one? Does everybody have a number? Yes? We have a number in mind? Okay. count to 3. I'm not going to say the 3. On the 3, say your number. 1, 2. Okay, I think I only heard 7s. So that has 7. So the only curve they threw here was bicyclics, which wasn't really a curve because it's bicyclic, so you automatically know how many rings you have. So, okay. So what I'm going to do is I'm in the process of editing this group, or editing this table to make it something a little bit more presentable. What it will have is it will have the structure, the name of that functional group, like C double bond OOH. It'll have carboxylic acid as to what the functional group is. It'll have what the highest, or what the suffix when it has the highest precedence, what it is with a acyclic system and with a cyclic system, and then it'll have what happens if it's not the highest priority, if it's a lower priority. And so then that table will be what we can use to put our names together. So what we really have to sort of focus on or think about is kind of how you handle each functional group that have these little idiosyncrasies, like amines, like esters. And then how, with the structure we have, how we put it together.
Are you going to write out, like, whatever's on the column to the left, or should we try to learn the bracketed version?
All the brackets mean is that carbon part of a chain, or is it part of a ring? Or is that carbon attached to a ring? That's all the bracket versus non-bracket means. Now, bracket oxygen means a C double bond O. So I'm going to write it out like what I wrote out here. That's what's going to be there. So if you say, well, do I have to memorize all the different carbonyl functional groups? Not if you're using this chart. You'll just see something with a C double bond OH. Oh, C double bond OH is an aldehyde. So you'll be able to do that. Hopefully as you do problems or study for this, it'll be a little bit more apparent. You know, it'll help you memorize or learn those functional groups. But this chart is going to contain the system by which we put our names together. The only thing that's missing is E and Z. That's the only thing that's missing in the naming. And so my conundrum for Friday is, and we are having class on Friday. Again, creativity saying, oh, it's not there, we must not be having class on Friday. I'll give you points for creativity. I will give you 0 points for accuracy. But then again, you guys, but as I'm copying the folders for each day over, there's more folders in the morning class and the afternoon class because I create the morning folder and then bring it over to you. So you didn't see anything there, so for all you know, there may not have been class on Friday. There is class on Friday, okay? And I could do two things. We could talk about EZ, but what I've decided to do is to hold off on EZ because that system, we're going to get to in about 2 weeks or so. So instead, what I will do is bring some naming problems. You can bring your questions about naming problems. And so Friday we'll do naming problems, and then that will be the end of naming problems. And then we will move on next Monday to Newman projections, and then into cyclohexane rings, and then into stereochemistry, So we're going to skip chapters 3 and 4 because 3 and 4 are some of these chapters that foreshadow stuff that I'm going to get to in 3 weeks anyway. Okay. So that's what we're going to do. I do have, and I will bring on Friday a couple suggestions about there are some free Android and iPad apps for phones or for iPhones that will help us with our Newman projections that use augmented reality. For that, it's pretty cool. But I've talked to the person who owns the company, and she's got National Science Foundation support, so that's why it's free, or I think one is 99 cents. But I just found out they had a chair one that they just created, so I'll give you the links for those for the free ones. All you have to have is just a phone that would work. But it kind of lets you model things without the Tinkertoy models. If you have the Tinkertoy models, great. If you need one, I have a few that I could loan you. But I just found that out yesterday, and I think her intern's been trying to get in touch with me, and I haven't been emailing back. But I spent like an hour talking to her at one of these conferences. Plus, we had a conference call at the beginning of last year, and I'm like, I don't know how to deal with the Top Hat book right now, so I can't throw in any more apps. I've got to deal with the book first, and I'm still kind of in that position. Some of these are games. They're couched as games because there's now an educational pedagogy called gamification, that we make our homework problems games so that people are motivated to do them and have fun. But these are really useful, so I'll bring that as well, so that on Monday that's how we'll start. So if you have any questions, email me, Piazza, or bring them to class on Friday.